start by discussing Galileo before we get into Sir Isaac Newton. People have been curious about the causes of motion for over 2,000 years, but a systematic approach to dynamics began only during the time of Galileo and Isaac Newton. The Greeks about the time of Aristotle observed that in everyday situations it requires a continuous pushing or pulling to keep an object such as a rolling stone moving. When the pushing or pulling is no longer applied, the stone comes to rest. The early Greek law of motion was simple. A constant force was required to produce a constant velocity. If the force was increased, the object moved faster. If the force was decreased, the object moved slowly. If the force was removed, the object stopped. These statements seem logical, but they are incorrect. Nevertheless, the assumptions that they were based on endured for nearly 2,000 years until the great Italian physicist Galileo explained the relationship between force and motion more accurately. Galileo devised two simple thought experiments about motion on inclined planes to explain his theory. In his first thought experiment, he reasoned that since a ball rolling down a slope speeds up, and a ball rolling up a slope slows down, then a ball rolling across a horizontal, non-sloping surface neither slows down nor speeds up, but continues to move with a constant velocity. Galileo did, of course, observe that a ball rolling along a horizontal surface eventually stops, but he assumed correctly that the ball was being slowed down by friction or resistance, as he called it. In his second thought experiment, Galileo reasoned that if the slope of the rising plane was decreased to make it less steep than the descending slope, the ball would roll farther along the slope, stopping when it reached the height from which it was released. The fact that the ball did not quite reach the height he attributed once again to friction. He concluded logically that if the slope of the second plane was zero, the ball once rolling would continue forever with no loss of speed in an attempt to reach its original height. This reasoning showed great imagination. After all, there is no such thing as frictionless surface. Also, it was a direct conflict of Aristotelian physics, which enjoyed general acceptance at the time. In contrast with previous beliefs, Galileo argued that it's just as natural for an object to move with a constant speed as it is for it to be at rest. Which gets us into Newton's laws now. Okay, so basically speaking, Galileo designed this experiment where he rolled a ball down a slope. And as it rolled down the slope, it of course speeds up, which makes perfect sense. And as that ball goes up the slope, it's going to begin to slow down. So what he initially suggested was that there is nothing affecting it on this horizontal slope. So the ball would just keep going in motion. But as he was working through it, he's like, okay, well, this isn't right, because this ball would go forever if he didn't have a resistant slope. The ball would come down and it should go forever. But then he said, well, there is some resistance, that resistance being friction. Okay? So that was the start of remember, for 2,000 years, everybody believed this was to be true. Okay, that this was not, before Galileo did his experiment, they believed that there was nothing affecting it, that it would just go on forever. Okay? So now we get into Newton's laws of inertia. Do you guys know what inertia is?
Yes.
What is it?
If it's in motion, it has energy, like a resistance to move.
Okay.
Like if motion will be carried out if you hit something and pull it.
Right. Okay, so if there's nothing resisting it, for example, somebody in a car accident, if they hit something head on, they would continue on with that same speed that the vehicle is in. What holds them back is your seatbelt. That's the only restraint that holds them back, and then your airbag, of course. But that person keeps going. So something is going to continue in the same motion unless there's a force acting against that motion. All right? And this is what we call Newton's first law, which is inertia. When no external, unbalanced force acts on an object, its velocity remains constant. Or, if no net force acts on an object, it maintains its state of rest or its constant speed in a straight line. So basically speaking, what they're saying is this. So if you have a car that has its cruise control set, let's say, it's just going to maintain that speed the whole way through until you either brake or you hit the accelerator. you have to add force to it to make sure that it stays in constant motion. It will stay there unless you brake or you hit the accelerator. Okay? No external unbalanced force acts on an object, the velocity remains constant. And then the second one is, this object here is going to remain at rest. That textbook is sitting on my desk right now. It's not moving. What is going to make this textbook move? It needs an unbalanced outside force acting on it. I would have to actually push on it or pull on it or lift it or do something to it from the outside. Okay? These are very basic laws. A magician pulls the tablecloth quickly out from underneath the place setting of expensive china. Due to their inertia, the dishes remain at rest where they are and are not broken. If a coin is balanced on a horizontal playing card on a finger, and the card is then flipped away, the coin, because of its inertia, will remain rest on the person's finger. So just two simple experiments. Alright?
You should try it.
You can at home. So that's the first law. So Newton's first law. We don't need to necessarily remember and memorize the laws, but we do need to know what the laws, how they affect things, how they affect what we're looking at in terms of equations. Newton's second law of inertia describes exactly how an object moves in the absence of any external unbalanced force. It moves with a constant velocity. It seems logical to assume then that when an external force is applied to an object, its velocity changes. Is there a direct, simple relationship between the force applied to an object and the change in velocity that results? Experiments can be devised to measure the change in velocity produced by various forces acting on different masses. Using experimental evidence such as provided by the investigation similar to the one at the end of this chapter, we can draw the following conclusions. Alright, so this is the one that we need to be primarily focused on because it leads it into our math part of this. When an external unbalanced force acts on an object, the object accelerates. The acceleration is in the same direction as the net force acting on the object. The acceleration varies directly with the net force applied. The acceleration varies inversely with the mass of the object. Okay, what do we need to take from this? Thank you. Net force. Net force is directly related to two things: the mass of the object and the acceleration at which the object is moving. So, net force. We're going to use this term twice. The first time we talk about it, we're going to talk about it as mass times acceleration. The second time we talk about it is we are going to take into account all of the forces that are acting and moving it in a certain direction, and all of the forces that are acting against that direction. So for example, do not write this down. Force applied is the applied force moving the object. We may have force of gravity restricting it. We may have force of friction working against it as well. Okay? So today, what we need to do is we need to take a look at an object such as that textbook right here on this desk. Alright. Currently, there are two forces acting on this object right here. It's not moving, but there's two forces acting on it. What are the two forces acting on that textbook right now?
Gravity.
Gravity. Gravity's pulling it down. What's holding it from falling?
The desk.
The desk. Do we know what we call that force? You guys remember?
Normal.
Yes. Very good. Very good. All right. First things first. The force of gravity is pulling it down. Okay? The normal force. This is new to most of you. The normal force. Force normal. Force normal is the force that acts perpendicular
Sorry, are we not supposed to write this down? We are.
this you can to the surface. So the force that acts perpendicular to the surface. Okay. So that's the first thing that we do. So if our surface is on an incline, for example, we're on a hill, the normal force still works perpendicular to it. It'll work at an angle. All right? Okay. I got to do one more thing here. What are the units on force? Newtons. Okay? So mass times acceleration, kilograms times meters per second squared are my units for both of those. And one of those is equivalent to 1 Newton. Okay? So 1 Newton is equal to 1 kilogram meters per second squared. Now, what we're going to do is we have to be focused on drawing out the forces, and we are focused on the vectors. Okay, so we're going to, again, using last unit, we're going to continue to work on this. Take a look at page 135. There's some pictures here on 135 I want you to look at. So when we draw these out, we don't have to draw pictures of the actual people. We can just use a box and then draw out what our forces are. Okay, so the first force, basically always acting, is the force of gravity. The force of gravity works perpendicular to the horizon. Okay, so that skier going down a hill, the force of gravity works in a direction perpendicular to the horizon. The normal force is the force of the hill pushing back up on it. Again, if I were to draw this down, that would make a right angle right there. The normal force is always the force acting perpendicular to the surface that we are on. Now, what direction is that box going to be moving? Be more specific.
Descending.
Yeah? How would you describe that to somebody, though? Yeah, you could. If you want to put directions on, you could. But I don't want to put directions on it. All right? What I want is that skier is going to be moving perpendicular with parallel to the hill. You agree? All right? Force of gravity is pulling the skier down. Normal force is pushing it back up, but there's still going to be a descent. So this force right here is moving down the hill parallel to it. That's the way the skier would move. Agreed? We're going to talk about the force applied. Force applied. The force applied is always going to be in the direction of the motion. The applied force will be in the direction of the motion. All right? Even though we have the force of gravity working down, this applied force works parallel. I'm going to just draw it down here as well. That makes that a right angle. This here is the force applied. This here would be your normal force, and this here would be your force of gravity. What have I created down below here? A right angle triangle. That right angle triangle is going to be used to help us solve the question. For right now, we don't need to do it. We just need to know the direction of it. All right, so the applied force is working in the direction of motion. I said the net force is your direction of motion force minus what's holding it back. What is holding the skier back? The friction. The force of friction. And the force of friction is working in the opposite direction of the motion. So in this particular question, or example, my net force is found by taking my applied force minus my force of friction. Okay? Alright, there's one more thing that we apply equation-wise on this, and that is this. I can calculate my force of friction by taking my normal force and multiplying it by the coefficient of friction. So that little micro f, okay, this represents what we call the coefficient of friction. Every surface has a different amount of friction to it. If I stop a car on asphalt as opposed to stopping a car on ice, all right, they're not going to stop the same way, are they? Because the coefficient of friction is different for them. And it's based on the surface. That will be given to you either on a chart or it'll be given to you within the question itself, the coefficient of friction. So we use it to help us solve. So today, basically what we need are three things. Net force is mass times acceleration. Net force is applied minus force of friction, or whatever's opposing it. We'll do pulley questions, they'll oppose it. Could be gravity. Something moving up, could be gravity. And then when we want to calculate our force of friction, we can use the normal force and times it by the coefficient of friction. Take a look at the bottom of 135. Or any questions? Sorry. Any questions about this?
It will MF after the force of friction, that's just a variable. It's a coefficient of friction.
The coefficient of friction. It will be given to you in the question or on a table. Which I said 2 minutes ago.
I know.
Do you listen again? Is that how that works? Lexi? Okay. Somebody pulling, you're going to have a number of questions like this. Somebody pulling an object such as a wagon, or somebody's pulling a toboggan in this case. So let's have a look and see what all of my... So this is what we call a free body diagram. Okay, so I have a toboggan. This person's pulling on this handle right here. Alright? Now, first thing I want to look at, what are all of the forces acting on just the toboggan itself for right now?
Gravity.
Force of gravity, pulling it down.
Normal.
What else is, what's pushing it up?
Normal.
Neutral?
Force normal.
Force normal,
Oh, normal.
the normal force. Okay? Moving along the snow, here's the catch. Alright, here's the catch for this question. We are going to assume that the toboggan is going to be moving parallel to the surface, right? This force right here will be what the pull force is. So that's what he's pulling on the handle. But the direction of motion is this guy right here. Oops, I did it again. Is this applied force. So your applied force is going to be in the direction of motion. What is going to affect that force? What's going to hold it back?
Friction.
Force of friction. Just like that. Okay? So even though I'm pulling on that handle, I'm pulling on that handle in that direction, the motion is still that way. Is there going to be some upward force? Yes. Now, if this thing is not moving and it's just sitting on the ground, what's the vertical net force? How much force would there be if it's just sitting there vertically? 0. Because the force of gravity is pulling it down, correct? And the normal force is pushing it up. So they're counteracting against each other. Therefore, your force net would be 0 for that, right? But you are going to have some little bit of vertical force here. We don't deal with this on all the questions. There's only a couple questions that we deal with this. But there would be some sort of vertical force pulling it up, which then means that the normal force and the vertical force are working in the same direction. But this is down the road. I'm not trying to overcomplicate this. I'm just showing you all of the things that are happening here. Okay? Questions about that? All right, we're not really doing anything yet. We're just kind of pulling it all together so that we have an idea. Okay? One of the very first things that you should do in all these questions is draw your free body diagram. It will go a long ways to helping you solve the questions. All right. Have a look at page 136. An object with a mass of 15 kilograms rests on a frictionless horizontal plane and is acted upon by a horizontal force of 30 newtons. What is the acceleration? Okay. So, an object with a mass of 15 kg. So we start this again. Just like in the first unit, we want to write out our given material, our given information. So I got a 15 kilogram mass, and it's sitting on a frictionless horizontal surface, and there's a force of 30 newtons acting upon it. That's a horizontal force. So I'm going to draw out my object. This, just like that, okay? All right. What are the forces acting on it to begin with? Gravity. Now we haven't done this, so let's do it right now. Let's calculate what the actual force of gravity is. Okay? So again, force is equal to mass times acceleration. Well, what's the mass of this object? 15 kg. What is the acceleration of gravity? 9.8 meters per second squared. Okay? Force of gravity is 147 newtons. So far, so good. What is the normal force now? Go ahead, Jake. Yeah. Depending on what we do. We could call one, as long as one's positive, one's negative. So if we're going to say this is positive, then I would say this is a negative 147 newtons. Okay? Alright, not important. We won't ask this. I'm just showing you, I'm going through all possibilities. This would not get asked in a normal question. I'm just showing you how we want to do it. Alright, so now there's a horizontal force of 30 newtons acting on it in a certain direction. We're going to say that direction is this way. That is my applied force. It's 30 newtons. Now, this is a frictionless surface. So is there anything holding it back? No, there's not. So, my net force is equal to mass, is equal to mass times acceleration. Yeah, I need that, sorry. Okay? So then what's my acceleration of this guy? Net over mass. 30 newtons over 15 kg. What's the acceleration? 2 meters per second squared. So far, so good. So this right now is all the new material for today. That's all the new stuff. Okay? Now I gotta go back and I have to take the 5 equations from the first units, from unit 2, and we gotta use them again. Okay? It says, how far will this move in 10 seconds? How far will it move in 10 seconds? Well, we have to write out V1, 0 meters per second. A, 2 meters per second squared. What else do I know? Time, yeah, 10 seconds. And I want my distance it goes. Okay? So again, you're going to need to get those equations out that you used, those 5 equations. Which one am I going to use that deals with V1, A, and T? How far did it go? 100 meters.
I got 98, but I did a much simpler method.
What did you do?
I just did 9.8 times 10.
9.8 times 10. Your acceleration isn't gravity though. Your acceleration is 2 meters per second squared.
But I still got real close, so.
But it's not even close to being correct. Because you can't use the acceleration of gravity because it's not moving up or down. It's moving horizontally.
I'm just going to write this one down.
Yeah, good idea. Okay, and the last part of this says, what will be the velocity? So I need to know V2, V1 plus A delta T, 0 plus 2 times 10, 20 meters per second. Okay? If you look in the margin on the page, it does show you the free body diagram of this. Okay? All of this right here on this page, it's all chapter 2 work. It's all stuff you've already done. Alright? This page right here is the new stuff, the force part. Okay? You good?
I'm very almost good. Okay, you're good.
I just have a question.
Yeah, Kelsey.
The force of gravity and the normal force, is always going to counteract itself?
If it's on a horizontal surface, yes.
Okay. But
Yes.
if it's,
But if you're on a slope, it's not going to completely counteract it.
okay.
Okay? We'll get into those questions eventually. But for right now, yes. Car with a mass of 1,000 kilograms. It's moving in a straight line at a constant speed of 30 meters per second. It is brought to rest in 25 seconds. What constant force is acting to stop the car? Okay. All right. First thing I do is write out what force is. What's my net force? Mass times acceleration. All right, so what do I need from this information? I need my acceleration. My V2 is 0 meters per second. So acceleration, 0 minus 25, so 30 meters per second, and that is over 25 seconds. What's my acceleration? Negative 1.2 meters per second squared. Force force equals 1,000 times negative 1.2, negative 1,200 newtons. Okay? That was a little easier, yeah, for sure. Okay, any questions so far? There's one thing that we do have to make a note of. Because force has acceleration in it. If an object is moving at a constant speed, there is no force acting on it. You have to be accelerating or decelerating in order for a force to be acting on it. So if it's moving at a constant speed, your force would be 0. Okay? Now this one was moving at a constant speed until we hit the brake. Therefore that brake made the force act against it. Alright? Any problems with that? This section is actually quite easy until you get into your vectors. A baby carriage with a mass 50 kg is being pushed along a rough sidewalk with an applied force of 200 newtons. And it has a constant velocity of 3 meters per second. What other force is acting on the carriage, and what is the magnitude of that force? Alright, so first thing we're going to do is draw our diagram. Okay? What is our forces acting on this? Force of gravity, number 1. Then?
Normal force.
Normal force acting against it. Yeah.
And force applied.
Force applied.
And friction.
And then some sort of frictional force.
Why is it force on this one?
Because it doesn't say that you're on a frictional surface.
So you just assume it's always there unless it says that.
Yes.
But that's just
Correct.
the opposite of the applied.
It'll be in the opposite of the direction of motion, which in this case is the applied. Yes. Okay, so those are what I have right now. All right. Net force equals. What's the direction of motion here? Which force is acting in the direction of motion?
Applied.
Force applied. And what's working against it?
The friction.
Force of frictional force. Force of friction. Okay. Now, I just finished mentioning this to you. How else do I find my net force? Mass times acceleration. And what is the acceleration in this question? What is it? 0. How come? Very good. It's moving at a constant speed, so that means then that this is 0 newtons. Okay? So your net force is 0. My applied force is 200 newtons minus my force of friction. So what is my force of friction then equal to? 200. In the opposite direction. Okay, so my force of friction will be equal to 200 as well. Any problems with that so far? I should put a negative on there. Okay, make sure that you know that it's in the opposite direction to the applied force, so you need to put a negative on it.
So the applied force is positive and the frictional force is negative.
Yes.
It's moving to the direction.
The applied force is always
So
working.
what if your frictional force is greater than your applied force? Then is the applied force moving?
Would it be moving?
Or moving backwards?
Your frictional force can't move it. It just moves, right?
I see. So they're all the same.
No. Okay, they're always the same if they're moving at a constant speed.
No, yeah,
Right.
so when we will be if the friction force is greater?
That's right. Okay, last question here says B. What value of applied force would be required to accelerate the carriage from rest to 7 meters per second? So V1, 0 meters per second. V2, 7 meters per second.
Time of 2 seconds.
Time is 2 seconds. And what is the question asking me? What value of applied force would be required to accelerate from that? Okay. So what am I getting from here? Acceleration. Okay, so acceleration is equal to
Change in speed.
7 minus 0 over 2 seconds. So that's going to give me 3.5 meters per second squared. All right. Now, again, net force equals applied minus friction, right? We're okay so far? Yeah? Here's where it's going to get a little bit tricky, the negative signs. It's going to get a little tricky on it, but whatever. Net force is mass times acceleration. So I've got 50 times 3.5 equals my applied force, which I'm looking for. What did I calculate as the force of friction on the sidewalk? Yeah, I'm just going to write it as 200 newtons. Okay? I'm not putting the negative in there because I'm not adding it. I have to keep it subtracting from the applied because it's working against it. All right? So now, what does the applied force have to be in this case? 200 newtons added on to 50 by 3.5. $375 newtons. Okay? All right, so far? All right. So, two things new to you today. Force net is equal to force applied minus force friction, and force net is equal to mass times acceleration. Those are the two things that are new to you today. Nothing else that we've done so far is different than what you haven't already done. All right? I'm going to do two more sample problems that involve the vector portion of this, and then after that I'll let you do the 5 questions on 138. Small boy, this is on page 139, small boy pulls his wagon of mass 24 kg, giving it a horizontal acceleration of 1.5 meters per second squared. If the wagon's handle makes an angle of 40 degrees with the ground, while the boy is pulling on it, and there is a frictional force of 6 newtons opposing the wagon's motion, with what force is he pulling on the handle of the wagon? Alright. So let's draw out our diagram here. First thing, acting on it. Do it the same every time. Force of gravity. What's acting against force of gravity? Normal force. Okay, here's where it gets a little tricky. The direction of motion will be horizontal. So that means that way. That's my applied force.
Well, so the direction of motion is the applied force.
Yes. Now, this is why it gets confusing. This is what I'm saying. But I also want to know what the force is he's pulling on the handle. That force there. That's what I want to know. My end game is this right here. This makes an angle 40 degrees. That's a right angle. Okay? And what is the frictional force? first things first. How do I find my net force?
Mass times acceleration.
Mass times acceleration. That's right. And applied minus force of friction. Agreed? Okay. What's the mass of the wagon? 24 kilograms. What's the acceleration it's moving at?
4.5 meters per second squared.
Jake, equals force applied. And then my force of friction is 6 newtons. So let's find out the force applied now. So how do I find my force applied? You think it is? 42? 1.5 times 24, which is 36. 36 adds 6 is 42 newtons. So there's my applied force in the direction of the motion of the wagon. That goes right here. Alright? How now do I find the force being pulled on the handle? Cos of 40 degrees is equal to 42 over my force. 27 newtons. There's your answer. Yes, Barry?
Sorry, I don't get why you didn't this. Are you trying to find the length of that?
I need this right here. That's my hypotenuse. This side's adjacent to that angle.
So you want the length of it? Like, I don't get why you want the length.
I want this. That's the force that I'm pulling on the handle. Okay, so I've got a wagon. Alright, can you see the wagon on the bottom of the page there? So the solid black line, that's the handle. Agreed? Yeah. So I want to know, what is the force that I'm pulling on this angle to get it? Okay? And the applied force though is in the direction of motion, which is the horizontal. Okay? So that's what I'm looking for now. Now, lots of these questions, they're going to give you this. They'll give you the force that's being pulled on, and then you have to find the applied force and do all of that after. But in this question here, they wanted you to find that force there. Alright? Anybody else have a question about that?
Yeah, I have one quick question.
Yes.
The second line under the F net.
Right here.
Yes. You say subtract 6 newtons,
Yes.
but you're supposed to add it.
It's working against the applied force, so I have to take it away from the applied force.
Oh.
So I don't do the same as the book. The book puts it in as an add and then makes it a negative. So it adds a -6. I like to do it this way because when I get into doing bigger problems, I want you to see that the applied force is subtracting anything that opposes it. Because we're going to get into pulley problems. And we have to know when to subtract and when to add. Okay? So in this case, I always write it as F minus whatever's restricting it. Alright?
So people aren't bad at math, it's just...
No, they're doing it a little bit different. I try and do it so I'm consistent, and this keeps me consistent with what we're going to do when we get into pulley questions. Yes.
What if the boy was pushing it, then would it be add?
No, because the friction's still working against it.
Okay.
Okay, yeah, so if somebody's pushing from this side, that's still the direction of motion, so I draw it out this way. Even though it's on the back side of it. This is what's happening. Where are all the forces acting on that guy? Or is the force being pushed this way? But the force acts against it still.
No matter what, you're gonna be adding it.
No, you can wait. You've got one more question this going to be.
Okay.
And then you can go after that. Any other questions about this guy? Because I'm going to get into one more that's a little more complicated than it.
So the net, F,
Mass times acceleration.
okay.
And mass is 24 kg. Your acceleration is 1.5 meters per second squared.
Okay. I see now.
All right, the last one is on page 140. This is the one that starts to get a little more complicated.
Mr. Newton, you can skip this until tomorrow.
No, I want to show it today and then I'll come back and do it again tomorrow. Two girls are trying to pull a 20-kilogram toboggan out of deep snow drift that provides an opposing force of 8 newtons. They are using ropes attached to the toboggan and parallel to the ground. The forces exerted by the girls and the directions in which they pull on the ropes are shown from above in this diagram. Okay, so what's happening is this. I have a toboggan. Now, I'm not doing anything with the force of gravity or the normal force in this case. I'm looking at this toboggan as if I'm standing above these girls and looking down on them. So there's one girl is pulling in a force in this direction right here. So that's F1, and she makes an angle of 30 degrees this way. So F1, and what's her force? 20 newtons, right? The second girl is pulling it this way. The angle is 20 degrees. And her force is 15 newtons. Okay? Now, we are intending on going in that direction. Right? We intend on going in that direction. And the force of friction is working against us with 8 newtons. Okay, so this is back to last chapter. When I look at this right now, is this toboggan going to go perfectly straight? How come?
Pulling a different force.
Because they're pulling in different directions with different amounts of force, right? Now, if these two things were the same, these two were the same, and these angles would be the same, they would move in the exact same direction, correct? Alright, so what I've got to do is I've got to determine, are they going to go up slightly or down slightly, based on my numbers. So what I'm going to do right now is I'm going to do the same thing that I did in the last section, and that's create a net table. I want to know the horizontal and the vertical for both of these pulls. So I'll put that right down here. Just because of the way I drew it, I'm going to say one's north, one's east, one's south, one's east. Okay, so here's how it works. I've got 20 newtons and 30 degrees right here. That means that this is 10 newtons up or to the north. Agreed? Okay, take the cos of 30 and times it by 20.
28.19.
No.
I got
Ow.
17.321.
17.321 newtons.
Backwards. Oops.
Did you divide or what?
I know, I did cos 20 times 30.
Okay. Oh yeah. So I've got that. So that takes care of what this girl's doing right here. The second girl is going in that direction. That's 15 newtons. That's 20 degrees. So let's do sine of 20 times 15. Sine 20 times 15. No.
5.130.
5.130, and that will be newtons south. Okay, and then take the cos of 20 times 15.
14.09 or 14.010.
And that's also going to be east. Okay. So now, what I'm going to do is create my final triangle to find out which direction the applied force is moving in. Now, if you look in your textbook right now, they add these two vectors together, and then they find it using the law of cosines. And then they subtract it's confusing. So if we just do this with one right triangle, we can get the applied force direction, and then we subtract our friction at that point. So I have 17.321 newtons east, and I have 14.010 newtons also east. I assume.
That's good.
And then I have 10 newtons to the north, and I have 5.130 newtons to the south. So let's add these two together.
31.041.
My calculator wasn't even on.
042.
No,
I started calculating and I have a calculator on.
331.
Sorry, I actually,
Right?
yeah, I actually put in a zero in.
Okay, and then right here I gotta subtract those two.
4.87.
That's to the north. Okay. Everybody got that written down? I need to change it a little here. Okay.
Yeah, I'm still.
Okay, so she's going east how much? 33.321. Is that right?
331.
331? Thanks.
I like the final countdown.
Okay, and what is it north?
Yeah, 4.87.
4.870 newtons to the north. So her applied force, their applied force, there's two of them. Their applied force is that right there.
I thought it was 31.331.
Is it?
Yeah.
Yes, it is. Okay. All right, so we've got to, again, just use Pythagoras' theorem and find the angle using tan. So what's her applied force?
Yeah, 31.707.
Okay.
It might be, you have to
Yeah,
give
I
a
think so.
little number.
Okay. And then I'm going east, and what's the direction?
Excuse me for the interruption. Page Allen to the office, please. Page Allen.
8.835. Okay. So there's the applied force the two girls are using to pull it in that direction. So they're going to continue to go up a little bit as they pull. They're not going to go in a straight line. So now to get the net force, what is my net force equal to?
Mass times acceleration.
Or,
The force versus
no, other way around.
oh, force applied.
Force applied minus my force of friction. So that's equal to 23.707 newtons east, 8.835 degrees north. There you have it. All right. Just a second. We're not quite done yet. We're not quite done. It asks for what is the acceleration. So to get the acceleration, how do I get it?
Net divided by mass.
Net divided by mass. So let's divide this number by your mass. What is the mass of that toboggan? 20 kilograms. So take this number divided by 20 kilograms.
And 1.185.
So your final answer, again, has to have your angle with it. Okay? So we are now, with this forces unit, doing all your chapter 2 equations, all of your vector work in chapter 3, and we're putting it all together with forces now in chapter 4. So you're combining everything that you've done up to this point. All right? Your question was what? Sam?
Oh, I don't know what you did.
What a
Yeah,
question.
I just read the angle.
Yeah.
Like, I don't get why you do that angle.
That's the angle I'm moving in. Always, it's always where your starting point is. Like if you're going to, yeah, like if you're going to explain this, you got to tell me, how do I go from here to right there? Right? So you're going to say, well, you got to go east first, and then you got to go 8.835 degrees to the north, and walk on that path, and you'll get to where you got to go. So that's why I always use the starting coordinate, or the starting point, where I draw my arrow. Okay?
So, how did you use acceleration of force divided by mass?
Yes.
Oh, I used the wrong force, okay.
All right, I'll come back at this tomorrow. Right now, you got the rest of class to do the 5 questions on page 138. Again, those ones are not vector questions, those ones are just using your chapter 2 equations. All right? You didn't do anything. Finished the test and that was it. Mm-hmm.